Welcome back to Neal on Fire, the podcast where we talk with innovators, leaders, researchers, and builders creating new solutions across the wildfire and climate technology landscape. I'm your host, Neal Spungen. Thanks for joining us. Today on Neal on Fire, we're exploring a breakthrough in swarm-based wildfire detection. As climate change accelerates fire frequency and scale, the early minutes and hours of a wildfire are more critical than ever. Our guest, Dr. Georgios Tzoumas, is a research expert and is focusing on improving a key search algorithm, the dynamic space partition method, by integrating an Archimedean spiral to dramatically increase coverage and resilience across massive landscapes, even on the scale of California. And we are going to be talking about all of those technical terms and breaking it down so we can all understand it. And we'll dive into what that algorithm means and why this improvement matters and what it could mean for future aerial detection swarms. Welcome, Dr. Tzoumas, and we're so happy to have you here today. First question for you. What motivated you to focus on improving wildfire detection algorithms using swarms of autonomous robots?
Well, first of all, Neal, thank you so much for having me. It's a pleasure and honor to be over here on the podcast, and very nice to meet you as well. Initially, I will have to start with saying that this piece of work is based on, many hours of research and interaction and conversation with firefighters around the world. So we've engaged with firefighters from nearly all over the globe. So firefighters from Europe, in Australia, in the States and the Americas. And what we were trying to understand is whether they see something like a swarm of drones being able to perform some sort of operation that's useful to them. And firefighters have been mentioning that it's very crucial to catch the fire at its early stages, so as early as possible. Of course, when we were running those studies, so that was about 25 years ago, some of the technological components were quite behind compared to the operational requirements that firefighters had. So what we were explaining to them is how would they feel if they had drones that would be larger, like 10-meter wingspan, that they could fly for 12 hours against high severity winds. And at the time, we were collaborating with a company called Wind Racers, that they've designed the platform similar to what we were describing to the firefighters. The reason why I'm making this introduction is because many people have a bit of a misconception of what drones are and what drones can be, right? Because currently most of us have in mind drones being these quadcopters that they can be quite large, but not as substantial in order to carry large payloads or to perform something very useful in the firefighting world, apart from just taking images or capturing, let's say, data, which is something that's very useful, of course. But nowadays, technology evolves and we see these sort of like hardware components become more capable to do other operations as well. So this is, let's say, an introduction about the drones, but you very nicely put what is the use of a swarm. Why do we need a swarm in this equation to help, let's say, firefighters fight fires or do any sort of operation? Well, swarms, and in case some people might not know what swarms are, they exist in nature. And we see them, let's say, in cases like flocks of birds flying together and doing weird shapes on the sky. The reason why this is important is that they don't really follow a particular leader. So the behavior that they have is what we call emergent. So they're based on the local interactions with one another. And then when, for example, two birds are flying too close from one another, they try to maintain a distance so that they don't collide. And that's useful because they create mechanisms that they can be quite scalable. So they operate with very simple rules, like the one I explained with if two drones are too close, then we need to be a bit further apart. And they create mechanisms that they can be quite scalable so they can have many, let's say, birds flying together. And this is the, let's say, the inspiration to design mechanisms that they work in a similar way. So in the case of drones for wildfires, there is a very high chance that some of these drones will need to sort of like land, let's say, change batteries or refuel, pick up some parts of the equipment. So when this happens, when some of the drones do something different compared to the main requirement of the overall fleet shouldn't, let's say, lose the operational capability that it has. So, for example, what this means in the firefighting world, if I have 5 drones in my hangar and they can fly and they can do something useful, which is fly for 12 hours and patrol for potential wildfires, and then look I've just finished servicing 5 more. Can I add them into that system? They can seamlessly go and interact with the other already existent drones that they're on flight. So that allows us to create a mechanism that A is scalable, so it can operate in larger, let's say, areas, and B, it can have different type of layers of operational capability. So a few of them can patrol an area, and some others would need, let's say, to even provide, let's say, fuel or medicine to someone, so do deliveries. So I'm trying to explain how versatile these operations need to be, hence why we needed to make swarms. And sorry, go on.
I was going to ask you, for the drones that you're talking about, are we primarily talking about surveillance, looking for an incident of wildfire, doing wildfire detection, or are we also talking about suppression where with drones that may be carrying either water or retardants or other materials?
Well, we're talking about both in this case. What we're designing as part of the university and the consortium that I'm part of is plug and play solutions. So we offer a software that can operate with any type of drone. For example, nowadays there are drones that can carry 100 of kilograms of payload or 150 kilograms. And then there are also other drones that can carry even 400 kilograms of a payload. So what we're saying is that if there is the potential to access that type of hardware, even from a fire service or a government or let's say an individual, we can use our software to integrate that specific piece of hardware on the general fleet. So that means that we are platform agnostic and we can allow any sort of platform to be used with the technology that we have developed.
So the algorithms that you've developed are primarily for the movements of the drones in a swarm formation.
Yeah.
You may have other providers that would have additional add-ins for suppression or for detection, but underlying all that is going to be the ability for these drones to effectively swarm and cover an area using the algorithms that you developed.
Yes, let's talk a bit about the algorithm specifically as well, since it's quite, well, in my opinion, interesting, and I hope you say so too. The algorithms are coming up because we need to provide the capability for a single operator to control multiple aircraft. That at the moment is not taking place in operationals, let's say fieldwork, due to legislative issues, boundaries of technology, etc. So in terms of requirements of firefighters, what they want is to be able to get as much meaningful data as possible in a specific, let's say, time frame and over a large sort of like scale scenario. So these algorithms are tasked to perform, let's say, some top level control of the drones, meaning you need to, over a specific area, you need to go towards these specific locations and start monitoring or patrol that specific area until you identify something that's meaningful. And then when they do, with AI algorithms that we have in order to detect fires using cameras, then they notify the user to explain, look, there is a chance that there is a fire over there. What do you think we should be doing? So apart from the algorithms themselves that control the drone, we also design and develop the user interface that allows that operator to interact with that mechanism. And we've done also loads of studies on this particular topic as well with firefighters because, well, operating a swarm is something that's quite novel, and operating it for firefighting elements, any type of operation, right? So even just go and identify or patrol an area is also something that has a specific touch of knowledge on its own. So we've interacted with 50 plus drone operators and firefighters to tell us how they would like this software to operate, how they would like to interact with it, and in order to be useful for the operations that they are called to address.
What about limitations? How many drones can you have in a swarm? And then also, are there specific types of drones or certain capabilities that are required to be able to use the software and operate in a swarm?
Well, the main element that we can do. So the main problem or the main challenges that we have at the moment in this space is legislation and, let's say, components where we can operate multiple drones at once. So the software can manage hundreds of aircraft of different types as well, because what we do in order to test that is we test, let's say, simulators, the same type of autopilots that we would use in the field, We operate them, but virtually, and we test these behaviors. So that can go up to hundreds of aircraft. When it comes to real world applications, it very much depends on the specific legislative bodies that we need to address. So every time we need to test stuff, we need to comply with Civil Aviation Authority rules or FAA in the case of the states, and to interact and explain all of these operations and how we need to mitigate risks. So the biggest hurdle for us is actually being able to do these sort of like steps in order to allow for operational capability, well, for legislation to follow the technologically ready products, let's say. So the other component, you mentioned a bit about the algorithms. Again, I'm going to go back a bit into the conversation that we've mentioned about the dynamic space partition. This is an example of multiple robots operating together. So with that algorithm, we've controlled, I think, more than 150 drones together, virtually again,
Wow.
right? Being able to sort of sporadically spread over an area and monitor that space.
You introduced an Archimedean spiral into the DSB controller. First of all, for those which may be many people watching or listening to this, explain what that is, and then we'll talk about what inspired that idea and what problem you were trying to solve and what the impact has been by integrating that.
Yeah, so we've talked a bit about the dynamic space partition. This is essentially what it does. It is that it separates the search space that we want to sort of like search for wildfires based on the number of available drones in the swarm. But when some drones would need, let's say, as I mentioned before, to land or do some different operations, the fleet arranges itself rather than going and asking the person who controls the drone to rearrange them. So that's the novelty of the algorithm. But that covers only the top part. So that means if I have, let's say, a fleet of 10 drones, how would I spread them over an area to identify a location of a wildfire? But the method of exploration, so after you reach that location, that let's say smaller part of the region that each drone needs to search on their own, they need to do something in order to search that space. And there are different ways that you can do it. There are, for example, ways that they are more stochastic, more random, like, for example, the random walk behavior, where your robot or drone just goes towards an area, and after a specific amount of time, it turns its direction. So this is a random walk. It's one of the most basic, let's say, swarm intelligence algorithms that we have. But there are also other methodologies that can be a bit more organized with less randomness within them. One of those is the Archimedean spiral. And the Archimedean spiral is creating, let's say, lines from a central location or a central area, expanding towards the outer regions of that area. So that means that our drone performs spiral at a specific distance from the lines of the trajectories that it makes. And that's what makes it an Archimedean spiral, because these lines are specific. They have a specific distance from one another. There are other spirals and these are all actually inspired by farming. Farming practices are doing that. If you see like the way even that pitches in some cases are being, are having their lawns mown, they have these sort of like spiral routes going around. So it's a very common way of covering an area, more or less. But there are other types of spirals as well, like the logarithmic spiral, which the difference is that the lines of separation between the trajectory of the aircraft are becoming larger and larger. So it kind of like expands. But this is not useful in the aspect of firefighting because the characteristics of the drones are quite specific. So if you have a drone that can see, let's say, 100 meters away to identify a fire, you would want to maintain that distance. If you increase, let's say, the size, that means that we don't have overlap. So some areas of that, let's say, region would not be covered. And chances are that the fire would exist there. So that's why we used that strategy. I hope I didn't confuse the audience too much.
No. So getting down to more practical application of this, I understand at the University of Bristol, one of the tests that you did with 30 robots, drones, using DSP with the Archimedean spiral, detected almost 88% of static fires. And so what does that level of coverage really mean in practical terms? Talk to us a little bit about that actual research that you did.
Well, the idea of this part of the research was to try and showcase that using, let's say, some aspects of autonomous solutions, we can have, let's say, elements of cost effectiveness. So using, let's say, 20 of these highly capable drones monitoring 24/7, some components are not that practical, right? Because I'm not expecting these swarms to be operational 24/7, for example. But days of high fire risk, let's say, I see the value of them being pre-deployed to search for fires when there is a high fire risk area involved. So the idea of this sort of like paper was to try and capture a reasonable amount of drones to be operational and to allow them to sort of like, let's say, showcase how they would operate within a day. So the idea was that within that sort of like specific 24-hour, let's say, simulation scenario, we would have 30 aircraft all separating the space of California and trying within that sort of like whole state to detect areas of interest, in this case, let's say wildfires. So the idea was that they would take off of specific bases around the area of California. They would self-organize, and we would simulate how this would work in a 24-hour operation of the drones. But of course, practically, this has loads of limitations at the moment. It's not that even if we would have, let's say, tomorrow, the capability, let's say we had 30 drones of that caliber ready to be deployed. As I mentioned before, there are so many regulative boundaries and at the same time elements that we need to understand before we deploy this tech. So the way that I see it practically working are smaller sort of like scale tests. So for example, of an area not as large as California, but of an area, let's say 1/10 of that area, we would be able to deploy those drones, perform these missions and bring data and information back to the operators that they're meaningful. And then we would start building that operational, let's say, capability. So you see, when we operate in research, we have this, let's say, idea on how this would work. But when it comes to real life deployments, reality is a bit different.
So you've mentioned California multiple times, and no surprise, lots of wildfires there. But
Yeah.
what are the limitations when you get to a very large area where you've got that high number of drones operating using the algorithm? Where does that break down? Where do you start to see some degradation in the system?
Well, the main element that we need to consider when we operate these aircraft are initially the hardware itself. So, for example, these drones will need to be capable at flying at very high speeds and being able to be quite robust when it comes to wind perturbations or, let's say, requirements to reload, whether it's batteries or whether it's fuel, depending on the drone. So one limitation is the actual practical hardware that these drones can have. The other limitation is communications. So in many cases, although we see, let's say, communications nowadays becoming a bit more, let's say, reliable, like, for example, satellite communication is now available that you can mount on drones and you can communicate with them over very large areas. These systems are sometimes quite heavy. So again, it falls back again onto, is my drone able to carry that type of communication module that can allow me to talk to these aircraft at very high or very far away from where my base is. And the other limitation, I mentioned it again a couple of times, which has to do with legislation. At the moment, for example, it's very tricky to fly within the aviation world what we mean beyond visual line of sight. So if you lose sight of the drone, and again, in some cases, it changes between countries, but still, even in the US, it's not that every operator has that capability. And in some cases, even trained firefighters who have the capability of flying smaller drones, they will still need to comply to that regulation as well. So it depends. In some cases, it changes, but I think that these are the main challenges. Now, I've mentioned a bit more on the challenges, a bit on the hardware, the capability, and when it comes to the actual sort of like software or implementation, I see that when we have the capacity to communicate with these aircraft, actually, the system itself is not that difficult to operate. So we haven't flown that system yet, or a drone that would be many kilometers away from our base so far. But we did manage to fly it at very sort of like long distances from where we were and still get the communication feedback that we wanted. So I have a feeling that the main hurdles in these operations are not actually the technological components, but it's more the integration and the framework on how you will need to operate them. That's the biggest issue for now.
I was interested to read that one of the most important elements of this is resilience, so that when you have a swarm and the swarm size drops from, say, 30 robots or drones down to 10, that DSP with the spiral still detects 70% of fires. So how does that work? And how is it possible that with a third the size of the drone swarm that you're still picking up three-quarters or so of the detection?
That's a very good question. It has to do with the way that we were assuming that the system would fail. What we're presenting in the paper is that after 12 hours of operation, we started, let's say, assuming that the drones would need to land, so that there was an issue with their hardware. So after 50% of the time, there was, let's say, a similar type of performance. And then afterwards, what we would see is that the system would again self-organize. And in some cases, areas that they have already been explored, they were covered by a percentage of the aircraft. But then the remaining ones would continue pick up some of the signal of the fires. What we've done there is show that we don't expect the system to start breaking straight away. So that would mean that we would have a system of drones of 20 aircraft straight away rather than 30 aircraft, right? So what we've done is, assuming that we had, let's say, 30 and 50%, let's say, starting breaking down for XY reason after half an hour of the simulation, we wanted to show that we would still get additional fires being picked up by the system. And the reason why this happens is because of the swarm intelligence scalability element that we mentioned before. So when some of the drones need to land, the whole system doesn't break down. Of course, its performance reduces compared to how it were before, but we can still have useful outputs from the overall system, which was the main sort of like purpose of choosing swarms to do that operation.
So, I'm sorry, if a drone goes out of service, the operator can put another drone back into the swarm. The swarm is automatically going to figure out where it needs to be and what function it needs to fulfill.
Exactly. Yeah. And of
Okay.
course, the exciting element is the fact, and I cannot stretch this enough, is talking with the people and with the users who are going to use this technology, because we didn't really come up with the requirements, right? We didn't say, oh, look, this is what you will need if a firefighting component is coming. But people were saying, in Greece, for example, there was a failure of a drone. And they were explaining to us, okay, so what happens if one of them fails? And some other people were saying, I've used drones in the past. I see that they can only operate with 40-minute battery capacity, the ones that they are commercially available now. So I would expect to see a behavior that they land and then the rest of the system can operate. So these were the conversations that they were key to try and define how the system would operate based on the requirements of the users. Because, I mean, I haven't flown a drone myself in a wildfire scenario. So this is very different compared to flying a normal drone in the field in a controlled space. So listening to what the users want was paramount to try and design these algorithms themselves.
How would you expect the algorithms to perform when fires are dynamic, spreading, or influenced by weather or fuel load? We talked quite a bit about detection, but what about when you're actually in a fire? How's that work?
Well, I can't disclose many things because we're working on some solutions at the moment as part of, do you know the X Prize competition? Yeah, so we're one of the 15 semi-finalists over there. So I won't be talking a lot about our strategy based on that. But what I can say is that what we're trying to design now is more hands-on elements, exactly what you said. Like, for example, if we have a fire, which is, let's say, it's starting small, but then it becomes as big as 2 by 2 meters, which is not a huge fire, still sort of like manageable. Can our system pick it up on time and deploy something that's reasonable and mitigate it around those sort of like timeframes and limitations? So these are the tests that we're doing now. And the good thing about the algorithms that we've designed, for example, the DSP, the dynamic space partition, all it does is that it positions drones strategically over an area, right? So we can adjust those areas of interest and these limitations that we have using the same logic. So, and that's the beauty of swarm intelligence, because we are trying to make controllers that they can be quite dynamic when something needs to change. If, for example, the available airspace reduces because, let's say, helicopters are coming by, and the integration with the helicopters can also be quite tricky. So the user can change dynamically the airspace that's available to the drones, and they will comply to move around these sort of like smaller areas. So we're doing those sort of like tests and components with our partners. We're trying to figure out when a fire takes place, and we're very lucky that we work with fire and rescue services. We work with the Lancashire Fire and Rescue Service that I mentioned. So the most tricky bit is, how do you test it if you don't have a fire, right? Well, the good thing is that with them, we can start fires in controlled ways, right? So we can test these components and these behaviors as we would want.
Where do you see this technology fitting into the broader wildfire detection ecosystem, including things like sensors and satellites and PTZ camera networks? Where do you think the sweet spot is for this technology?
The drones in general, for me, they have an aspect that's quite different compared to satellites or sensors, which is actually the mitigation if needed, right? So the drones that I believe that they're useful, they can be useful in different parts of the operational capability within the wildfire ecosystem. For example, let's say, I will try and simplify it, but in the aspect of wildfires, we have, the preventive component, we have the actual incident, and then we have the post-incident elements. Drones can have operational capabilities in all of these three stages. For example, in the prevention, they can fly, as I mentioned, in days of high risk, given that they have the hardware capability. And when they detect a fire, to mitigate it as fast as possible. There are high chances that this is not going to be successful, right? So the fire would be, let's say, would develop, and then we would need to do something with more traditional means. If, for example, the integration with crewed aircraft doesn't work well. But then, assuming that this is not going to be useful anymore for limitations that we've just described, there is another window of opportunity, which is what happens post-incident. So in many cases, and especially at components where there is, when nighttime falls and fires become sort of like more prone because temperatures drop and winds are also dropping, depending on the scenario. Then there is a chance that drones can fly again and mitigate the fire, or to identify even hotspots, because they can fly at night, they can provide that component of intelligence. And that is something that is not very, at the moment at least, satellites are not able to provide as much. So there is a gap between the temporal and the spatial resolution that satellites provide. For example, in terms of information, I mean, at the moment, I think we're in some levels of the world in turnarounds of hours, which is pretty good. But when it comes to operational elements, as you very rightly said, seconds and minutes count a lot when it comes to wildfires. So there is a space over there that drones could operate from an informational perspective, but also there is an overall advantage that drones have the capability to actively do something on the field rather than just sensing.
I understand that this is still in the research phase. When do you see this becoming commercially available, and what will that look like? How will you go to market with this?
I would say it's a bit of a tricky, let's say, element to try and have as a plan, because there are so many variables still. Naively, let's say 5 years ago, I would say, oh, in 5 years, I see them drones flying and performing operations. Now that I've been in this space for a while, and I see these technologies being actually quite welcomed, but at the same time, in some cases, the overall infrastructure not being ready to access these capabilities. So what I'm trying to say is that drones in some cases are quite more expensive compared to what firefighters can afford, or in other cases, firefighters are not trained to use them the way that we need them to be used, or the technology develops so fast that the infrastructure is just not ready to accept them. So I would say that over the next 3 to 4 years, I would expect to see some operations taking place in very specific scenarios, right? Like, for example, what I said about potentially operating in post-incident components and patrolling for hotspots. It's something that firefighters would want, and that's sort of like one of the uses that Lancashire Fire and Rescue have sort of like mapped out for us. So there are these certain scenarios which I think that they will operate sooner rather than later. And then after these operations take place, maybe in the next 6 years, we can start seeing them operate more broadly. But as much as I want to be optimistic, in general, we also need to be pragmatic. So in many cases, we need to sort of like accept and understand and see the limitations of the technology. And we need to maintain the levels of collaboration with the people who will use them so that we can understand more how these tech should be deployed.
For the firefighter who's watching this, is excited about this technology and wants to learn more, is there an opportunity for a proof of concept? Is there some phase coming up where you're open to testing in
Yeah.
the local?
There is. At the moment, we've done a big round of tests with our partners in the fire and rescue service scene. So overall, we're trying now to find out who would be interested to try and shape potential projects. So by all means, I would welcome any sort of like person who would like to talk about this technology or to see how they would like to integrate it to just reach out, and I will try and respond to try and make some pilot sort of like projects that are meaningful to them as well.
That's great. We'll be sure to include your contact information in the show notes here. I want to thank you, Dr. Tzoumas, for a really interesting discussion today. I, for one, learned 2 new terms that I wasn't aware of before, and I'm sure our audience will be the same way. So it's always good we can pick up some new technology and something that'll help in the wildfire fight. So thank you so much for that. And I think this conversation shows just how much innovation is still ahead in wildfire detection and response, and advances like enhanced swarm algorithms can meaningfully change how quickly we identify and contain fires in the years to come. So thank you so much for joining us today, and we'll see you next time for more wildfire innovation discussions on Neal on Fire.
Thank you so much for having me, Neal. Thank you.